clusters are so beautiful that we tend to focus on them. We tend to look at them because we like them. But you need to know that, this is, it's like economic justice. The rich clusters, and even the loose clusters, give us at most 3% of the galaxies in the universe. And 97% of the galaxies in the universe are in poor clusters or smaller things. And in fact, it's yet another example of the case of cosmic mediocrity, the Copernican principle. The loose group that we live in, the Milky Way and M31, is the typical system. Most galaxies live in such loose groups, not even in the somewhat bigger groups that you sometimes see. So, galaxies live in groups. They're self-gravitating and bound things. The Coma cluster of galaxies is more than 100 times more distant than the Andromeda galaxy, just to give you an idea, is away from us, to give you an idea of what the scale is here. Now, I told you that the idea that dark matter is not baryonic really only took hold in the early to mid-1980s. Yeah, I would say mid-1980s. And before that, people looked to see what else the matter in clusters of galaxies might be if it were not in the form of galaxies. And there was a very, very interesting false alarm. That false alarm occurred in the early 1970s. In 1971, an X-ray satellite called Uhuru measured X-ray emission from the Coma clusters of galaxies. It's interesting because the Uhuru mission was meant to look at stars within our own Milky Way. And the discovery of X-ray emission from clusters of galaxies came as a surprise, as a bonus. Astronomy is like that. There are lots of bonuses. So the question is, first of all, what is the emission mechanism? And it's an emission mechanism that we've actually discussed before. The idea is if you have a positive ion, and if you have an electron, and that electron is traveling past the positive ion, it gets deflected by its electrostatic field. Now, if you're changing its velocity over here, that's an acceleration, and so it will radiate a photon. And such photons are called Bremsstrahlung, which I'm told means braking radiation, as in putting your foot on the brakes. You're swerving over here when you put your foot on the brakes, but you're accelerating here, and an accelerating electron produces photons. And Bremsstrahlung usually refers to the X-ray case. We've actually discussed this before in the context of stellar opacities within stars. The inverse of this process, a photon comes in and gets absorbed and changes the direction of the electron, is what we call free absorption. And the process is of interest in both directions, both when the photon is absorbed and when the photon is emitted. Here's the case that's emitted. These electrons, it's a very hot, it's a very hot plasma on the order of 10 to the 8th degrees Kelvin, and so the velocities and the wavelengths are in the X-rays and not in the optical region. Now, let me tell you that there is nothing mysterious about Bremsstrahlung. We have calculated the radiation from electrons under various considerations as they're accelerated, and we could, the electron in the spring. We could do this too, but you would hate me, because once you say that the power is 2/3, they use the Larmor formula. They give 2/3 times e squared over c cubed, and times the acceleration squared, and calculate it, then it's just nasty arithmetic after that. So I'm not going to do it. I'm just going to give you the formula, and I ask you to trust me that I'm giving you the correct formula. I think I am. So I'll give you the formula for the emissivity which is going to have the units of ergs per second, per cubic centimeter, per unit frequency. And if you're sharp, you'll notice that the per second cancels out the per unit frequency. So it's energy per unit volume. So this emissivity, epsilon sub nu, free, is given by, do I have enough room for this? Barely. Okay, we'll write it over here. Epsilon sub nu sub free is equal to, there are a bunch of factors of 2, actually 2 and 2 to the 11 halves, it turns out. There's a pi to the 3 halves. I told you it was a nasty calculation. There's a 3 to the 3 halves. There is a kT. I said it would have the units of energy. The scale of the energy is set by the temperature of the plasma, kT, so that's the scale of what goes on. There's a term that looks like this. The rest mass energy of the electron divided by kT, the thermal energy, to the 3 halves power. And it's kind of interesting. The hotter you get, the less Bremsstrahlung you get. And the reason is the harder it is to deflect that electron. That's the less acceleration you get. You know, whatever your electrostatic force is, if it's moving, if the electron's moving faster, it takes more impulse to deflect it. So you get less Bremsstrahlung when it's hotter. There's a term over here that looks like E squared over MEC squared, this quantity cubed. This over here is the classical electron radius. We saw that in the Thomson formula. And then finally, there are 2 factors here. N sub I, the number density of our ions. N sub E, the number density of our electrons. There is an e to the minus h nu over kT, because it's a thermal plasma and you can't get electrons that are moving infinitely fast. And finally, if you throw in the effects of quantum mechanics, you get yet another one of our so-called Gaunt factors, G sub free of nu and t, and these are factors of order unity that deal with quantum mechanics, and that you don't get from the classical calculation from which I've saved you. So there we are. There's our free emission formula. Save this if you're going to go into the field, because it's actually quite useful. We can take this and integrate over all frequencies. E sub nu free d nu is equal to 1.44 times 10 to the minus 23. I'll call this thing over here lambda prime. It's got units of ergs per second per centimeter cubed, because we've integrated over frequency now. And then we'll take the temperature and divide it by 10 to the 8th Kelvin. So this quantity here is called T8. It is dimensionless. This is raised to the 1/2. We'll take rho, the density of whatever it is, divide by the mass of a proton, quantity squared. And this gives us our, and I guess this must be rho is proof. This is ergs centimeters cubed, because this has some per centimeters cubed in here. So it's ergs per second times centimeters cubed. And this will give us the right units. So I hate using this notation. I very much prefer keeping the constants in here rather than writing some number out in front. Because putting the constants in here gives you some idea of what the physics is. It makes sense that the volume over which you're going to get substantial free radiation is on order of the classical electron radius. You know, if you're beyond the classical electron radius, then you're not going to feel that ion there. So that makes sense that it should have that power cubed here. This is a little bit trickier here. This comes from the fact that fast-moving electrons aren't reflected. So we know how much Bremsstrahlung to expect from various, for a given amount of plasma. If we know the density of the plasma, we can calculate what to expect. Now, so let's make a model for our clusters of galaxies. What have we got over here? Good. Clean blackboard. And we can ask ourselves, in our model for the clusters of galaxies, one way to do it is to say pure dark matter. Well, actually, the model for the cluster of galaxies will have 2 components, each of which is an isothermal sphere. There'll be an isothermal sphere of Bremsstrahlung emitting gas, where we have rho sub gas is equal to rho G0, the central density of gas, plus R over RC quantity squared, all raised to the 3 halves. Now you'll say to me, oh, Professor Schechter, but eventually it goes as 1 over r cubed. That's r squared. That's true, but because we're going to have 2 powers of rho g, one for the number density of ions and 1 power of the number density of electrons, most of the contribution is going to be coming from the center of the cluster of galaxies. And so making this approximation doesn't lose us that much. We're missing a bit of emission from the outskirts, but it won't matter much. We can also say, on the hypothesis that it's in the form of dark matter, rho dark is equal to rho dark 0 over 1 plus r over r c, assuming that these are coextensive and so have the same functional form for their variation. And in particular, in the case of rho dark, we can go back to our definition of what the scale length was, RC, the core radius. The core radius is something you can measure by looking at the fall off of the X-rays as a function of distance, because we know how the density in an isothermal sphere varies. We know what this functional form is, so we can look at how the X-rays vary. We have that rho dark 0, if it were, so I guess the way to put this is to say, we'll take the case of either or. Either it's 100% gas or it's 100% dark, or you can think of rho dark 0 as being total. So we have rho dark 0 is given by 9 sigma squared over 4 pi g rc squared. Under the assumption again that this is isothermal, and this comes, rc is 3 times our definition of alpha. So this gives us the central density of dark matter. Now, the total luminosity that we get from this is given by the integral of E sub nu free d3r times which is going to have 2 powers of density in it. This integral is going to be equal to r lambda prime times r T8 to the 1/2 time divided by mp squared, and then inside the integral we'll have integral 4 pi r squared rho g0 squared over 1